Okay, thanks, Rogerio. So let's get started. So let's start talking a little bit about supersymmetry. So what is supersymmetry? Supersymmetry is a symmetry that quote unquote rotates bosons into fermions and vice versa. Right? So schematically, what you have is, so when you do a supersymmetric transformation, and I'm being very schematic here, okay? The idea is that you do a supersymmetric rotation, it takes a spin zero particle into a spin half particle, and the same transformation acting on the spin half particle rotates it into the spin zero particle. Okay, that's being pretty schematic. I'm not showing any indices or anything, for example. But already this is enough to see that this can help with the hierarchy problem. Okay. So the logic is this. So by definition, if supersymmetry is a symmetry of the theory, supersymmetric transformations have to commute with the Hamiltonian. And that's what it means to be a symmetry of the quantum theory, right? So now let's consider the operations of the Hamiltonian and supersymmetry acting on a spin zero particle at rest. Okay, so imagine doing this sequence of operations on a spin zero particle at rest. All right, and so let's first do it in this order: supersymmetry first, and then Hamiltonian. Then we'll consider the same transformations, but in the opposite order. All right. So you do a rotation on the spin zero, a SUSY transformation of the spin zero, you get a half. And the Hamiltonian acting on a spin half particle at rest just gives you the mass. So you get the mass of the fermion. Okay? You get the mass of this fermion. Now do the same transformation, but in opposite order. So the Hamiltonian acting on a spin zero particle at rest gives you the mass of the spin zero particle. And then supersymmetry acting on the spin zero particle gives you the spin half particle. Okay. So this sequence of operations gives you this, and this sequence of operations gives you this. Okay. But remember that these operations commute. So this has to be equal to that. And so you can see that for this to work, the mass of the spin zero particle has to be equal to the mass of the spin half particle, right? So in other words, if there is a supersymmetric transformation that relates a spin zero particle to a spin half particle, those two particles must have the same mass. Okay, there's no way out of that. Okay, so that means in the supersymmetric theory, for every boson in nature, there is a fermion with the same mass. Okay, that just follows out of the pretty much the definition of the theory, right? Now, just with that much information, we can see how supersymmetry can solve the hierarchy problem, right? Now, the supersymmetric partner of the Higgs boson is something called the Higgsino. The Higgsino is a fermion, so its mass is protected by symmetries. It's protected by chiral symmetry. Yeah, so just like the way the mass of any fermion is protected by chiral symmetries, the mass of the Higgsino is protected. But now, since supersymmetry says that the Higgsino and its superpartner, which is the Higgs, right, they must have the same mass, it means the mass of the Higgs is also protected, right? So this is the way that supersymmetry addresses the hierarchy problem. Supersymmetry says that the mass of the Higgs and the mass of the Higgsino must be the same. The mass of the Higgsino can be protected by chiral symmetries. And once the mass of the Higgsino is protected, the mass of the Higgs is the same as that of the Higgsino, and it's also protected. Okay? In a little while, we'll see how that works in terms of diagrams. Okay? But for now, this is just the underlying logic. Right? Okay. So the minimal supersymmetric extension of the standard model is called the minimal supersymmetric standard model. Okay. And it's usually known by its initials as the MSSM. Okay. The particle content of the MSSM is shown below. So here's what it is. So for the gluon, the superpartner is the gluino. For the W plus minus and W3, the superpartners are the vinos, okay, pronounced vino, not wino. The superpartner of the B, right, the hypercharged gauge boson, is the bino. The superpartners of the leptons are the sleptons. The superpartners of the quarks are the squarks. And something interesting happens with the Higgs. So naively, you would think, well, I have a Higgs and one Higgs in the standard model, so I need one Higgsino. But remember, the Higgsino is a fermion, and you have to think about anomaly cancellation because the Higgs has a hypercharge, and the Higgsino will have a hypercharge. And if you just have one Higgsino, the anomalies are not going to cancel. So the theory is not going to be consistent at the quantum level. Okay. So that means you have to have two Higgsinos, and so you have to have two Higgs fields. Okay. So the minimal supersymmetric standard model has two Higgs doublets, not one. Okay. And that's because you need two Higgsinos for the anomaly cancellation to work. And this kind of works well because remember in one of the earlier classes, I told you that if you have two Higgs doublets, you have to be very careful about flavor changing neutral currents. It turns out that in the MSSM, this up-type Higgs, that's one of the Higgses, gives mass to all the up-type quarks. And this other Higgs, H down, the down-type Higgs, gives mass to all the down-type quarks and the leptons. Okay? And since this guy doesn't talk to the down-type quarks, and this guy doesn't talk to the up-type quarks, there is no flavor changing neutral currents. Okay, so it's a type 2, it's what's known as a type 2 Higgs doublet model. Right? And of course, you also have a super partner for the graviton, which is called the gravitino. And this is just what I said earlier. You need two Higgs fields to cancel the anomalies. And one of the Higgses gives mass to the up-type quarks, the other to the down-type quarks and leptons. All right. So once electroweak symmetry is broken, the bino and the third component of the vino, W3, and the neutral components of the Higgsinos all mix with each other. They are all fermions, and they all start mixing with each other once you break electroweak symmetry. So the mass eigenstates are called the neutralinos. Right? And similarly, once electroweak symmetry is broken, the charge components of the vino and the charge components of the Higgsino start coupling to each other. They mix, and the mass eigenstates are called the charginos. So usually in supersymmetry, you don't usually talk directly about the bino or the vino. Usually you hear them talk about the neutralinos or the charginos because the mass eigenstates are all mixed up. All right, so now let's kind of understand how the hierarchy problem is being solved at the level of diagrams. Okay. So this is the top loop. This is the usual top loop that you're familiar with in the standard model. It's the biggest contribution. Contribution to the Higgs mass is from the top loop. And now the reason this is cancelled is that there are now new particles which are the superpartners of the top quark. They're called the stops. Okay, these particles are called the stops. They're the superpartners of the top quark. Okay. And there's now a new diagram that contributes to the Higgs mass that involves these stops. Okay. And these diagrams have different signs because remember, this is a closed fermion loop. So it has a minus sign. And this is a scalar loop. So relative to each other, there's a relative sign. Because this is a closed fermion loop and that's a scalar loop. Okay? And this vortex is related to those two vertices by supersymmetry. Okay? And so these two diagrams actually cancel. The quadratically divergent part of these two diagrams cancels very nicely. Okay? And there's no quadratic divergence left over. On the other hand, we haven't seen the superpartners. Okay? So, you know, we know that there's no new light particle with the, you know, scalar particle with the mass and charge of the electron. Okay? There's no such particle, right? And so what that means is that even though supersymmetry says that the superpartners have to have the same mass as the standard model particles, so that cannot actually be true. So it means that supersymmetry cannot be an exact symmetry. It has to be a broken symmetry. Okay. And if it's a broken symmetry, then the masses of these particles needn't be the same. Okay. But then supersymmetry isn't an exact symmetry anymore. And so this cancellation is no longer exact. Okay. In the exact supersymmetric limit, this cancellation is exact. Okay. But now this cancellation is not really exact anymore. And but the point is that as long as so what happens is that this quadratic divergence is now cut off at the mass of the stop. Okay. So remember, I was regulating this using a hard cutoff. That hard cutoff is now the mass of this stop. Okay, and so that means the stop can't be very heavy. Okay, because if you made the stop very heavy, you would basically get this quadratic divergence back now cut off at the mass of the stop. And we saw that already for the top loop, if it's cut off at 1.5 TeV or something, already there's a problem. There's a tuning at the level of 10% or worse. Okay, and so that means that for this cancellation to work, for the hierarchy problem to be solved, these superpartners can't be very heavy. Okay? They have to be around the TeV scalar, and even better if they're lighter than that, right? And so this is kind of the great promise of supersymmetry. It promises you a solution to the hierarchy problem. And it also tells you that the particles which are solving the hierarchy problem cannot be too heavy, otherwise the solution doesn't work. Okay? And this is why when the LHC was about to turn on, so many people were really excited and thought we were going to discover superpartners immediately. And that hasn't happened, right? Which is one reason why there hasn't been that much work on supersymmetry maybe in the last 5 or 6 years. Okay? But there is an important set of ideas here. And it still could be correct at the level of more complicated model building, or it's just slightly beyond the reach of the LHC or something. Okay? And so yeah, okay? So it is important to know these things. Let me stop here and ask if there are any questions.
Okay. First, I have to apologize. My internet is unstable, so I was disconnected for some moments, and then I came back. So if there were some questions, maybe they were raised. I just see one question right now from Sudipta, which I don't understand. Maybe he can clarify. And the question is, then what will be the symmetry with that you have started? Maybe Sudipta can clarify this question. Or maybe there was a previous question from Sudipta. Okay, so while Sudipta is preparing, clarify, there are more questions. So Anupan is asking why we don't take supersymmetry as an exact symmetry.
So if supersymmetry was an exact symmetry, there would be a scalar particle with the same charge as the electron and the same mass as the electron. And we know from experiment that there is no such particle. Okay. Because it would be a really light particle. It has electric charge 1. We would have produced it in colliders, couples to the photon, but we have never seen any such particle, so we know it does not exist. So supersymmetry cannot be an exact symmetry.
Right. So I think Siddhartha is explaining what was the question before. So is there any supersymmetric model where particles, many fermions and bosons and its superpartners have different mass? Then what will be the symmetry with that you have started?
No, so the idea is you start with the symmetry and with an exact supersymmetry and you spontaneously break it. Okay.
Yeah.
So yeah. So trying to think of an example off the top of my head. So think of say the top quark and the bottom quark, right, before electroweak symmetry breaking. So before electroweak symmetry breaking, before the Higgs gets a wave, they are both massless, right? And in fact, there's an SU2 symmetry that rotates the left top into the left bottom. But once electroweak symmetry is broken, they get different masses, right? So the idea is something like that. So if supersymmetry was before supersymmetry was spontaneously broken, all the standard model particles and the superpartners would have the same mass. But once supersymmetry is broken, that gets split, all right? And then their masses are different, right? Just the way the masses of the top and the bottom get split after electroweak symmetry breaking.
Okay, and Sanket is asking, can you repeat why this top mass is the cutoff, was the cutoff for the integral, for the divergences?
It's only the cutoff for the quadratic divergence. Okay, and to see that in detail, you actually have to look at these diagrams. Okay, so I claim that that these two diagrams, I claim they would cancel. They would cancel exactly in the limit of exact SUSY. Okay, and well, let me be careful. I want to be very careful here. So this diagram will contribute to wave function renormalization and to the mass. I claim the contribution to the mass would cancel exactly between these two diagrams. Okay, in the limit of exact supersymmetry. But what happens when you give these guys a mass, the scalars a mass, is that the contribution to the mass doesn't cancel exactly anymore. Okay, and you get a quadratic divergence back, but that is now cut off at the mass of these scalars. Okay, to see that in detail, you actually have to work out the diagrams. Okay, it's not obvious.
Okay, so Taekim, he's asking, how do you manage D term and F term if you redefine into neutrino or chargino? So I'm not sure I understand this question. Do you understand this question?
Yeah, so that's a little bit more detailed. So the thing you got to keep in mind is that so if you're writing the Chargino mass matrix or the Neutralino mass matrix, so there's a contribution from the so just remember, just think of the way the gauge field appears. Right, you have a gauge covariant kinetic term, right? So the Vino, etc., are gonna appear in that way also, right? They kind of appear in there. So it's not, you can't really just see it from the F term and D terms. Okay? It's more complicated than that. Okay? You have to look at the kinetic terms, the gauge covariant kinetic terms of the Higgs. Okay, supersymmetrized. Okay, and that's more work than just looking at F terms and D terms. Okay, sorry, for people who don't understand, that's a slightly detailed question about supersymmetry.
Okay, and Sudipta is asking, can you explain again why 2 Higgs doublets are needed?
Yes. So let's say you started with just one Higgs doublet, and then you would have one Higgsino, right? Now, usually this Higgs has a hypercharge of +½ So this Higgsino would have a hypercharge of +½ also, because the supersymmetric transformations commute with the gauge charges. Okay? So every particle and its superpartner have the same gauge charges. Okay? So this Higgsino would have hypercharge +½ right? But then you have a fermion with hypercharge, right? You have it's not vector-like, so you're going to end up with an anomaly. Okay, so the anomalies won't cancel. The anomalies of hypercharge are not going to cancel. Okay, so this theory is not consistent. So to make the theory consistent at the quantum level, you have to cancel the anomalies, and so you have to add one vector-like fermion, so one fermion which is vector-like with respect to that. So these are a vector-like pair, and so the anomalies will cancel. You can write a mass term for these two guys so that they are vector-like. Then this guy will have hypercharge -½ So yeah, so the anomalies will cancel, then the theory is consistent. But then the superpartner of this guy means that you must have a separate second Higgs. So it's a 2 Higgs doublet model.
Okay, so I don't see any further questions. So this is the time you should make the joke, Chacko, about supersymmetry. But no, we're too harsh on supersymmetry. So half of the particles of supersymmetric, half of the particles in supersymmetric models have already been discovered. A little bit less because they're 2 Higgs doublets. So.
That's right. A little bit, all the particles, half the particles -1.
Half the particles -1. Sorry, there's one more. Sorry, there's one more question by Francesca. How can we get the SUSY electron so massive?
It turns out not to. It turns out in realistic models, it's not too difficult. See, the trouble is usually the opposite one, right? To keep a scalar light is hard, right? Because there are quantum corrections, right? So the minute you break supersymmetry, immediately all the scalars will float up. Okay, it just happens. Even if you try, the hard part is to stop them from floating up too high. Okay. So yeah, that's not the problem.
Okay.
All right.
Okay, Chacko, just move on. Thank you.
All right. So in the standard model, baryon number and lepton number are accidental symmetries. And we discussed this at some length. However, they are not accidental symmetries of the MSSM. So to avoid large baryon and lepton number violation, we usually impose an additional symmetry known as R parity. And this is how R parity is defined. Okay, it's some complicated definition in terms of baryon number, lepton number, and spin. But the only thing you really need to know about R parity is that once you impose R parity, both baryon number and lepton number are exact symmetries. Okay, not the lepton flavor symmetries, but the baryon number and lepton number are overall baryon number and overall lepton number are symmetries. So under R parity, all the standard model particles, including both the Higgses, have even parity, and all the superpartners have odd parity. Okay. So immediately, the moment you impose R parity, there's a prediction, which is that the lightest supersymmetric particle has to be stable. Okay, because it has R parity minus, and it cannot decay to just standard model particles because those all have R parity plus. Okay, and R parity is conserved, so just one minus can't decay to a bunch of pluses, right? So once you impose R parity, the lightest supersymmetric particle has to be stable. So then if the lightest supersymmetric particle is stable, and if it's neutral, it could constitute the observed dark matter, right? Maybe that's the dark matter, right? Okay, so then let's go back to our list of what are the particles in here that are neutral and which could play the role of the dark matter. Okay, so let's go down this list. The gluino has color, so that's not good. But there is the neutral vino here, W3. There is the bino, okay. And of course, those guys mix into the neutralinos. And there's inside here, there's a sneutrino, okay, the super partner of the neutrino sitting in here. There's a sneutrino, that guy is neutral. There's two neutral guys in here, right? Again, they mix with the bino and the vino, right? They are neutralinos. The neutralinos in here, right? And this guy, the gravitino. Okay. So let's see. Let's go down. So the candidate particles in the MSSM to play the role of dark matter, the sneutrino, the gravitino, and the lightest neutralino. Okay. Whichever of these is the lightest, that guy could play the role of the dark matter. Okay. And hundreds of papers have been written on each of these, okay, studying them in detail. So there's another very important consequence of R parity. R parity means that all supersymmetric particles must be pair produced in colliders. Okay. In other words, since the standard model particles all have even R parity, so you're beginning with an initial state with even R parity, the final state must also have even R parity. And that means you can't produce just one supersymmetric particle, because then you'd end up with a final state that was R parity odd. So you must produce at least two supersymmetric particles, okay? At least two. You can produce 2 or 4 or 6, but obviously kinematically 2 is preferred. And so there is no single production of supersymmetric particles in theories with R parity. Okay. All right. So once produced, each superpartner, okay, will now decay down, okay, and it will eventually decay into a bunch of standard model particles plus the lightest supersymmetric particle. Okay, so that means that every event which produces supersymmetric particles at a collider will actually produce two of them, or some even number, and so you'll end up with at least two of the lightest supersymmetric particle. Okay? And if the lightest supersymmetric particle is the dark matter, it's going to be invisible at colliders. It's just going to stream out. Once it's produced, it's just going to fly through the collider. It's invisible. So it's kind of almost like a neutrino or something. Okay? And since supersymmetric particles are pair produced, we are going to have two of these lightest supersymmetric particles in every signal event. So, so the characteristic collider signals of supersymmetry with R parity involve missing energy. Okay, so this is why there's so much attention being paid at the LHC to signals with missing energy. Okay, historically, right? Because that's the classic signal of supersymmetry, and it's also, of course, the classic signal of dark matter. Okay, and of course, in a SUSY theory with R parity, those things come together. Okay, they marry each other in a very nice way. Okay? And so this is why, you hear people talk about jets plus METs at the LHC, or dileptons plus MET. Okay? These are classic signals of supersymmetry, and people have spent years of their lives trying to optimize those searches. They're trying to reduce backgrounds and do the most accurate kinematic cuts. All right. Okay. So R parity has another important effect. R parity also explains why the corrections from supersymmetric particles to precision electroweak observables are small. Remember, every supersymmetric particle is odd under R parity. And so that means if you're looking at a correction to the W boson, let's say to the Z boson propagator, okay? Now you're integrating out this heavy supersymmetric particle, and you're looking at a correction to the Z boson propagator. But you see that because of R parity, you can't, there's no tree-level diagram involving the exchange of supersymmetric particles. The supersymmetric particles can only come in loops. Okay? So the effects of supersymmetric particles on precision electroweak observables are all loop suppressed. Okay? And that means it's a lot easier to satisfy precision electroweak constraints. Okay? And it's pretty soon we're going to be looking at composite Higgs theories, which don't have this feature. And there you're going to see that precision electroweak has real teeth. Okay? But in SUSY, usually, because the corrections to precision electroweak are loop suppressed, usually once the superpartner masses are a few hundred GeV or something, it's not a big constraint. Okay? The collider constraints in SUSY are much more powerful than the precision electroweak constraints. All right, so supersymmetry does with R parity does some amazing things for you, right? It can solve the hierarchy problem. It can give you the dark matter. It suppresses flavor changing neutral currents, right? Okay, and it kind of does that, without too much stress. Okay, but there are some things which are not automatic. Okay, there's certain things which are automatic in the standard model, which are not automatic once we are talking about supersymmetry. Okay? So one thing which is not automatic is that in general, you get large flavor changing neutral currents. Okay? So we had a big discussion on this in the standard model. You have a GM suppression, you have CKM suppression of flavor changing neutral currents in the standard model. In the MSSM, you don't have any of that. Okay? You still get a loop suppression, But you don't, but in general, you don't get a GIM suppression or a CKM suppression or anything like that. You get your loop suppression, that's it. Okay? And that's way too big. Okay, that's way too big unless there's some kind of alignment between the masses of the scalar superpartners and the fermions. Okay? So you need some flavor alignment. You can't, a random SUSY theory is going to give you big flavor changing neutral currents. And there needs to be some serious model building to get around this problem. Right? Another thing which is not automatic is CP. So in general, in the MSSM, there are large new sources of CP violation. Okay? And this is called the SUSY CP problem, right? The previous problem, the flavor changing neutral currents, is called the SUSY flavor problem. Okay? So SUSY has a flavor problem and it has a CP problem. Right? So a large part of building a realistic SUSY model, right, is finding a way to solve these two problems, the flavor problem and the CP problem, right? And the last time I lectured at ICTP, which was 6 or 7 years ago, I spent quite a lot of time talking about various mechanisms to solve these problems. Okay? But this time I want to talk about different stuff. I'm more excited about stuff that's happening now in the community rather than older stuff. Okay? But I'll just tell you the rough idea. So usually what a typical SUSY model looks like is you have some kind of a hidden sector that spontaneously breaks supersymmetry, okay? And usually it does it dynamically, right, through strong dynamics. And then you have some sector that transmits supersymmetry breaking from this hidden sector to our world, right, the visible sector, right? And the spectrum, you know, the masses of the supersymmetric particles of the MSSM superpartners depend on exactly how supersymmetry is transmitted from the breaking sector to us. So depending on how that supersymmetry breaking is mediated to us, that determines the masses of the superpartners. Okay? And the key thing is it has to be done in a way that doesn't give you, that solves the SUSY flavor problem and solves the SUSY CP problem, okay? And these are serious problems. There's not that many ways known to do it. It's not, there's maybe 5 or 6 ways that actually work in detail, right? And so examples are things called gauge mediation, gaugino mediation, anomaly mediation. Okay, these are a few of the examples, but there's not a lot, right? And so this is a, so this is a, this is usually a serious constraint in building SUSY models. But each of these mediation mechanisms is very predictive. So you get a prediction for the spectrum of, you get a prediction for the spectrum of the superpartners, right? Okay. All right. So one last slide on SUSY. Okay, so I told you all the good things, right? So let's move forward, you know, to the present day. Okay. So most simple supersymmetric models are severely constrained by the data and are fine-tuned at the percent level or worse. And there are 2 reasons for this. The first has to do with the value of the Higgs mass, 125 GeV. And the problem is that this is well above what is expected in most simple supersymmetric models. Okay? So At tree level in the MSSM, there's actually an upper bound on the Higgs mass. The Higgs has to be lighter than the Z. Okay, so this is a sharp prediction in the MSSM at tree level. Okay, the Higgs has to be lighter than the Z. So if you want a Higgs mass of 125 GeV, you need to put in large radiative corrections. Okay, and usually those radiative corrections will involve the supersymmetric partner of the top quark, the stop, okay, because that's the thing that couples most strongly to the Higgs. Okay, and so usually to raise the Higgs mass using quantum loops all the way up to 125 GeV, you need the stop masses to be in the few TeV range. Okay, and remember that it's the mass of the stop now which is cutting off the quadratic divergences. Okay, so once you have a stop mass in the few TeV range, that's bad. That means you're getting order a few percent fine tuning immediately. Okay, now this prediction that the Higgs mass is lighter than the Z is a prediction of the MSSM, the minimal supersymmetric standard model. So you can get around this prediction by going beyond the minimal model. Okay, but usually that needs some serious model building. Okay, it's not completely obvious to get around this prediction. So it's not a given at all. Okay. All right. A second source of fine tuning, okay, comes from the fact that we now have direct LHC bounds on the stops, okay, the superpartners of the top. And they have to be pair produced. Okay, so it's not easy to produce them. It's not that easy. They have to be pair produced. But still, the bounds are at the level of 800 GeV or higher. Okay, and eventually, as the LHC keeps going, it's going to be higher than a TeV probably if they don't find something. Now, okay, you might say, well, that's not too bad. The quadratically divergent contributions to the Higgs mass parameter are cut off at 800 GeV. That's not too bad. But if you look at it in detail, what really happens is that you no longer have a quadratic divergence, but you still have a log divergence. Okay, and you get a correction to the Higgs mass that's proportional to the Higgs mass squared. That's proportional to the stop mass squared. But now you get this log here. Okay, so what happens is when you put in the stop, okay, you do get rid of the quadratic divergences, but you're left with a log divergence. Okay, and you might say, well, what is this lambda here? Lambda is the scale at which supersymmetry breaking is mediated to the visible sector. Remember, in those models I showed you, there's some sector that mediates supersymmetry breaking. So lambda is the scale of that at which that mediation happens. And in any realistic model, it's like 100 TeV or higher. Okay, and so you put in 800 GeV here, put in 1000 TeV or something there, and you start seeing that you're tuned. You need fine tuning at the few percent level to reproduce the observed value of the Higgs mass. Okay, and that's not good. Okay, and these are hard problems. Okay, and it's not so easy to get around them. Okay, which is why in the last, say, 5 years or so, there hasn't been that much work on SUSY compared to some of the other ideas I'm going to talk about. Right. So I'm going to end here on SUSY. Okay. This ends our discussion of SUSY. Are there questions?
Yeah. Sudipta is asking where our parity comes from.
Okay. So usually we just impose it by hand. Okay. Usually we just say that our parity is a symmetry. So in addition to supersymmetry, our parity is also a symmetry, and we just impose it by hand. That's what we usually do. There are some models, usually left-right models, in which our parity emerges as an accidental symmetry. Okay? There are some clever models in which our parity is an accidental symmetry. but usually is just imposed by hand. Okay.
So I think there's a follow-up by Sudipta. Is this a smart choice?
How should I put this?
Well, you avoid
Okay,
proton.
let me put it like this, okay? We know the protons don't decay quickly because we are all alive, okay?
Yes.
If you don't put something like R parity, the proton will decay. Now the thing is that there are some things you can do. Let me take that a little bit more seriously. You can relax R parity, but you better do it in a way that you preserve either exact baryon number or exact lepton number. Because if you break both baryon number and lepton number, the proton will probably decay quickly. Okay. So there are models that people build that don't have R parity. Okay. Those models are there, but usually they preserve either baryon number or lepton number. Okay. Because there's a tremendous constraint from proton decay. We know the lifetime of the proton is 10 raised to 33 or 34 years. Okay. And that's a very difficult bound to satisfy if you're violating both baryon number and lepton number. You can violate one of them and the proton will be stable, but you can't violate both of them. Okay? So usually if your theory doesn't have R parity, you'll be sure to preserve at least one of baryon number or lepton number. And you can do that, and those theories are interesting. You probably won't get dark matter because now the lightest supersymmetric particle can decay. You have to think about position electroweak. There are many things you have to think about now. Okay? The collider signals are very different. Okay? There are hundreds of papers written on R parity violation. So, okay? But most SUSY models, people do like to keep R parity because it gives you dark matter and it solves a bunch of issues in one shot.
Okay, I don't see any further questions. So Chacko, please go ahead.
All right, very good. All right, so now let's come to composite Higgs models. So the idea here is that the Higgs is just not an elementary particle. Okay? It's just not a fundamental particle. Okay? It's some composite made together by gluing together more fundamental constituents. Okay? And since the Higgs is not an elementary scalar, the quadratically divergent contributions to its mass are cut off at the compositeness scale. Okay? So there are quadratically divergent contributions to its mass, but above this compositeness scale, which we call lambda, the Higgs doesn't exist. Okay, maybe all you have is elementary fermions, which at high scales and at low scales they glue together to form the Higgs. Okay? So at high scales there's no Higgs, and so there's no sense in which it has a quadratically divergent mass. And so the quadratically divergent contributions to the Higgs mass are cut off at the compositeness scale lambda. And so if we can make lambda low enough, okay, we have solved the hierarchy problem. Okay. All right, so now the question is, okay, the big question is, how low can we go? How low can you make lambda, right? And remember, the Higgs is a strongly coupled composite. Okay? It's a strongly coupled composite. Okay? And so it's going to have pretty big self-couplings. Okay? Think of the pion. Once you start, at low energies, the pion is weakly coupled. Okay? But once you start scattering at energies of order GeV, which is the compositeness scale of QCD, the pion is very strongly interacting, right? So the pions are Goldstone bosons. They're derivatively coupled at low energies. But once you start scattering at energies of order the compositeness scale of the pions, they're strongly coupled. And so similarly for the Higgs is composite. At the compositeness scale itself, interactions are going to be big. It will have large self-couplings. And so at those scales, you're going to get operators like this. Okay, this is a dimension 6 operator divided by the compositeness scale. And there is no symmetry. You can convince yourself there's no symmetry that can ever forbid this operator. Okay. Now the question you got to ask yourself is, I gave you a basis for dimension 6 operators that only involve the Higgs and things like that. So there's some way of rewriting this in that basis. Okay. And my claim is that there's many ways you can contract indices in this kind of an operator. But imagine that I write a combination where this mu and nu are antisymmetric. So put a commutator here and put a commutator here. Now the commutator of d mu and d nu is the gauge field. Okay, that's the way, for example, Peskin and Schroeder defines the gauge field as the commutator of d mu and d nu. Okay, and so if you have a commutator here, you get a gauge field, and if you have a commutator here, you get another gauge field. And remember our old friend OS. OS was H dagger sigma, H dagger Pauli matrix H W mu nu B mu nu. So that is hidden in here. Okay, this operator contains that guy. Once you rewrite it appropriately, integrate by parts, you will massage it, use the equations of motion. You'll find that operators like this contain OS, which contributes to the S parameter, right? Since you all did the homework, you know that it mixes the Z and the photon and is constrained by positional electroweak, right? And you can do some estimate, some methods of naive dimensional analysis to estimate what this coefficient is. And then you find this is order 1. And then you look up your positional electroweak constraints on the S parameter. And you find that the compositeness scale has to be above 5 TeV, right? Now, this is far above the Higgs mass of 125 GeV. Okay, so position electroweak is telling you, no, you can't bring lambda below 5 TeV, okay, unless you tune positional electroweak as well. Okay, positional electroweak is telling you you can't push the compositeness scale below 5 TeV. Okay. On the other hand, the Higgs mass is only 125 GeV. Okay, and so that's a potential problem. And to explain this, we usually take the Higgs to be a pseudo-Nambu-Goldstone boson. Okay, so we usually say the Higgs is something like a pion. It's a Goldstone. It's a composite Goldstone boson, right? And that explains why it can be at least somewhat lighter than 5 TeV. Right? So this is the idea, okay? And this is the approach I'm going to follow, okay? Because this is the approach I'm going to be following. I'm going to take the Higgs to be a composite pseudo-Nambu-Goldstone boson of some strong dynamics. All right. So okay. Now in the standard model, the Higgs, apart from giving mass to the W and Z, it also gives mass to the standard model quarks and leptons. Okay? So there has to be a mechanism for the Higgs to give masses to the standard model quarks and leptons. Okay? And there's more than one way to do it, but I'm only going to discuss one method, which is called partial compositeness. Right? This is, I think, by far the most efficient mechanism. So rather than give you a bunch of words, let me illustrate it for the case of the up-type quarks. Okay. What we do is we include in the Lagrangian terms of the form So this here Q is the left-handed doublet of SU2 left. And UC is, the SU2 singlet quark in the standard model. So we write terms that couple the quark doublet of the standard model to some operator. This is an operator O, okay, of the strongly coupled sector that has the quantum numbers opposite to those of the quark. So this operator has quantum numbers that make it, that allow you to write a term like this. Okay, so it has the quantum numbers that are the opposite of Q. And similarly, this is an operator of the strong dynamics that has quantum numbers that are opposite of those of UC. Okay. So OQC and OU are operators in the strongly coupled sector, okay, from which the Higgs emerges as a composite. So the idea is that once you reach the composite in a scale, this OQC, this operator of the strong dynamics, it has overlap with resonances, which have the quantum numbers which are fermions, which have so this term becomes a mass term for Q with a resonance of the strong dynamics, and this term becomes a mass term for UC with a resonance of the strong dynamics, right? So this thing has the quantum numbers of a resonance like this, and this thing has the quantum numbers of a resonance like this. So once you reach the composite in the scale, you're going to get mass terms like this, right? And now remember, the Higgs is part of the strong dynamics. So the Higgs is going to have couplings to these resonances, right? I'm sorry, this should be a QC. Okay, there's a typo here. There should be a QC. Okay. So the Higgs is going to have couplings like this because it's part of the strong dynamics. And there's also going to be, these are resonances, so they're going to have masses from the strong dynamics. And the idea is that when you integrate out these heavy resonances, okay, they're going to so the idea is when you integrate out these heavy resonances, you're going to get a Yukawa coupling for Q and UC with the composite Higgs. Okay. What's happening is that the standard model quarks Q and UC are mixing. So once you have both this interaction and this interaction, what's going to happen is that this quark in the standard model is going to mix with this resonance, and this UC is going to mix with this resonance. And since these resonances have a Yukawa coupling with the composite Higgs, because of the mixing, the standard model quarks are going to get a Yukawa coupling with the Higgs. Okay, so the fermions of the standard model are now partially composite. Okay? And through their partial compositeness, through their mixing, they obtain Yukawa couplings with the Higgs. Okay, this is what's going on. Okay, so let me stop there and ask if there are any questions so far about composite Higgs so far.
I don't see any questions right now, but I can ask a question.
Mm-hmm.
When you write down these operators that couple to standard model quarks,
mm-hmm.
Can you say something about the naive dimension of these operators? If they have to be, there's any hint of, at some point they, yeah, go ahead.
So let's say a little bit about that. So, so the question is, okay, so So this O, right, it has to be a singlet under the new strong dynamics, right? Because our quarks are singlets under that dynamics. So this has to be a singlet under the new strong dynamics, right? And that's the, and if the dimension of this entire thing is bigger than 4, so that this is non-renormalizable, in the IR, these couplings will be very, very small. Okay. So we need the dimension of this operator O to be, since Q has dimension 3/2, we need the dimension of this operator O to be around 5/2 or less. Okay. Otherwise, this will flow. To become irrelevant in the IR. Okay. So the dimension of this operator O has to be 5/2 or less. All right. Now, so it's not necessarily easy to find a theory where you have operators like that, okay? Because this is a fermion, and it has to be a singlet of the strong dynamics. And so if you start with a UV strong dynamic, a UV theory which has only fermions, then when you make a fermion singlet, it's not gonna be, it's gonna have dimension more than 5/2. So this is one reason why very often you believe that you need to assume that this thing has dimension less than 5/2. And so probably some strongly coupled conformal field theory or something like that. Something which in which it's easy for the dimensions of operators to be, of fermion operators to be potentially less than 5/2, right? So it may be a strongly coupled CFT which maybe just doesn't have a weakly coupled description entirely in terms of fermions or something. So one is making some assumptions about the dimensions of operators here, right? And yeah, and this is where the ADS CFT correspondence comes in, because the extra dimensional RS models have CFT duals, and so choices about the dimensions of operators like this become choices about the bulk masses of fermions in the RS model. So this scenario is fairly straightforward to realize in Randall-Sundrum models. Whether it's actually realized in nature is a difficult question. Okay? We don't know any actual example, but that's also could be because we don't know a lot of strongly coupled conformal field theories. Okay? So yeah, so this could happen, but we don't actually know a concrete conformal field theory which does exactly what we want.
Thank you, Chacko. Are there more questions for Chacko? I don't see any questions in the chat. Any more questions? Can raise your hand too if you want. Okay, Chacko, just go ahead.
Okay, so in realistic composite Higgs models, the Higgs is usually identified as the pseudo-Nambu-Goldstone boson of a global symmetry that is spontaneously broken by the strong dynamics that generates the Higgs. Okay. But what that means is it's very important to have a detailed understanding of the properties of Goldstone bosons in general. Okay. Because the low energy properties of the Higgs are gonna be strongly tied to the dynamics of Goldstone bosons. Okay, so we need to have a detailed understanding of the properties, of the properties of Goldstone bosons in general. So what I'm now going to discuss is how to write down the low energy effective Lagrangian for Goldstone bosons based on symmetry considerations. Because you have some strongly coupled dynamics, which is breaking some global symmetry and giving you the Higgs. Okay, what that strongly coupled dynamics is, it could be very complicated, right? But on the other hand, the Higgs is the Goldstone boson, and it's gonna retain some properties of the that show its Goldstone boson nature. And so we need to have a detailed understanding of the properties of Goldstone bosons, right? And so let's do that. Okay. So let me discuss how to write down the low energy effective Lagrangian for Goldstone bosons based on symmetry considerations. So I know Ricardo did a little bit of this last week. Okay. So hopefully that'll be helpful. Right. So consider a scalar field phi with a U1 symmetry. Okay. So this is just an elementary scalar field with a U1 symmetry. And let's say that the potential for phi has the usual Mexican hat form. Okay. So it looks like this. My Mexican friends call this the gringo tourist in Mexico hat.
I think wine bottle is more politically correct.
Yeah. But yeah, they say no Mexican actually wears a hat like this. But so yeah, so here's the Mexican hat potential. We can expand phi about the minimum, and here's what we find. There's a radial mode, and there's the Goldstone mode, which corresponds to the Goldstone mode corresponds to fluctuations along the bottom of the potential. And the radial mode corresponds to fluctuations along the steep directions, right? But there's a flat direction, and the Goldstone mode corresponds to fluctuations along the flat direction. Under phi goes to e raised to I alpha phi, you can see just from the definition of theta, phi goes to e raised to I alpha phi means that theta is shifting as theta going to, actually there should be an F here, it's a typo. Theta goes to theta plus alpha F. So the global symmetry is realized non-linearly through the shift of theta. Okay. So the symmetry hasn't really gone anywhere, okay? In the sense that this is still a symmetry of the Lagrangian. Okay? The vacuum no longer respects this symmetry. Okay, but at the level of the Lagrangian, this is still a symmetry. And the low energy Lagrangian is going to respect this symmetry. Now, in the low energy theory, the radial mode will not be present because it's heavy. So only the massless Nambu-Goldstone mode theta of x will be present in the low energy effective theory. The Lagrangian for theta x must respect the shift symmetry. So it must respect the shift symmetry theta of x going to theta of x plus alpha. Now, the shift symmetry means that, you think about it, it means that only terms with the derivatives are allowed. Only terms with the derivatives of theta are allowed. So you can write a kinetic term for theta. And then you can write terms with additional derivatives like this. Okay. And there are higher order terms. Okay. But every term is going to have a derivative. If you write a term without a derivative, it will not satisfy the shift symmetry. Okay. So the low energy theory for the Goldstone boson is derivatively coupled, right? Now there is an unknown coefficient C1 here, and in principle we can determine what C1 is, okay? Because we have the full theory here, and so we could integrate out this radial mode. We could integrate out this radial mode and determine the coefficient C1, okay? But the crucial observation, okay, the crucial observation is that any theory, right, any theory with a global U1 symmetry that is spontaneously broken will have a Goldstone boson theta x that satisfies this shift symmetry. Okay. So the form of the effective Lagrangian is completely dictated by symmetry. In other words, here we started from a scalar, elementary scalar field that had a Mexican hat potential. And from that, we can integrate out the radial mode and find the form of this potential. But the claim is this. Okay, the claim is a very powerful one. Any theory, it could be a strongly coupled theory, whatever, in which leads to the breaking of a global U1. Okay, so that the only light field is a Goldstone boson. In any theory like that, the Goldstone boson is going to satisfy this kind of a shift symmetry. Okay, and so the form of this Lagrangian, is completely dictated by the requirement that the Lagrangian for theta has to satisfy the shift symmetry. The only difference between all these different theories that can break a U1 is in these coefficients. Okay. C1 is not going to be the same in our Mexican hat theory as in some strongly coupled theory that breaks the U1. Okay. Or if you have a theory with two scalars, okay, that couple to each other and break the symmetry, the value of C1 you're going to get is not the same as in this theory, okay, in general. Okay. So the only thing that, so you could have a very, very complicated theory full of strong dynamics that breaks the U1. But in the end, the only differences between our simple Mexican hat and that theory is going to be in the values of coefficients like C1 in these derivatively coupled operators. The form of the low energy Lagrangian is completely dictated by the requirement that this shift symmetry must be satisfied. So this is just what I was saying. Different ultraviolet theories will lead to different values of the coefficients in the Lagrangian like C1. But the form of the terms in the Lagrangian are completely fixed by symmetry. Now, let's say C1 is order 1. Okay. Then this theory is going to become strongly coupled. Okay, this is a non-renormalizable theory. It's going to become strongly coupled at a scale of order 4 pi f, if C1 is order 1. Okay. This theory will become strongly coupled at a scale 4 pi f. And so that means the theory is not well defined. If you try to scatter, Goldstone bosons with momentum more than 4 pi f, okay, the theory won't describe it. Okay. So that means that new physics must enter below 4 pi f. Okay. And that could take in many different forms. It could be as simple as that Mexican hat scalar model that we were talking about. It could be that simple. Okay. What this is saying is that then the mass of the radial mode has to be less than 4 pi f. Okay. But it could also be the new physics that comes in, could be some very complicated strong dynamics. Okay? So the only thing the low energy theory tells you is that new physics has to come in before 4 pi f. Okay? It tells you new physics has to come in. It doesn't tell you what that is. Okay? It could be as simple as your Mexican hat, but it could be far more complicated. All right. There is an alternative way to obtain the low energy effective theory for the Goldstone bosons that's often more convenient. Okay? So one way would be to start from shift symmetry and write down everything consistent with the shift symmetry. Okay, and that would work, and you could certainly do it that way. And for example, if you open the amazing textbook by Weinberg, that is what he does. Okay, you know, it gets more complicated once you have a non-abelian symmetry. Okay, but Weinberg shows you how to do it, and it's completely correct, of course, and you can do everything this way. Okay? But the way I'm going to show you is a lot of times it's simpler and more convenient. And so I'm going to show you how it works for the case of U1 breaking that we have been considering. Okay? So we know there's this object theta of x, okay, that shifts, right? Consider this object phi hat. And, so you stare at it, oh, isn't phi hat exactly like phi? Remember earlier we had a phi. And here's phi. And compare it to phi hat, and you'll see the only difference between phi and phi hat is that phi hat doesn't have this radial mode. Okay, so phi hat is just phi where I've thrown away the radial mode. Right now, so the advantage of working with phi hat is that it transforms linearly under U1. So when you do a shift, when you do a phase transformation, okay, theta goes to theta plus alpha f. Okay, phi hat rotates like e raised to I alpha phi hat. So it transforms just like phi did, right? And you guys have a lot of experience in writing Lagrangians which are invariant under phase transformations. Okay? You've been doing it since you were, since your first field theory class or whatever. Okay? So you know how to write Lagrangians with this thing. I could teach you how to write Lagrangians with this thing, but I'd rather let Weinberg do it. Okay? I think he's smarter than I am, a lot smarter than I am. Okay, but this one, all of us know how to write Lagrangians with this. All of us know how to do. So okay, so now to obtain the low energy Lagrangian for theta of x, simply write down the most general Lagrangian for phi hat of x consistent with this rephasing symmetry. Okay. Now the first thing you notice is that if you write a term without any derivatives, like you write phi dagger, phi hat dagger, phi hat, this is certainly invariant under this. But that term will not contain theta of x at all. Okay, so you can write it, but it's not going to give you anything. The only terms that will contribute are terms which have derivatives acting on phi hat. Okay. So you can write a kinetic term, or you can write a term like this. And then what you do is, after writing down all these invariants, you just expand them out. You just expand phi hat out in terms of theta x. Okay. And here's what you're going to find. When you expand it out, you're going to find that you get exactly those terms that I wrote earlier. Okay. You're going to find that you get exactly these terms. Okay. There's going to be what you'll see is that every term that you could write based on this, you can also write out in terms of phi hat. Okay, and so you can either start with theta and write terms which are invariant under this, or you can start with phi hat, write terms which are invariant under this, and then expand those terms out in terms of theta hat. Okay? And whichever way you do it is going to give you the same answer, right? Okay, so so let me stop here and ask if there are any questions.
Right. I just see one question by Sudipta, and the question is, why the radial mode is heavy?
Why the radial mode is heavy? If you minimize this potential, okay, you minimize this potential, find the vacuum and expand about the vacuum, you'll see that the radial mode has a mass 2m squared. Okay, just do it. That's what you'll find. You'll find that the radial mode has a mass 2m squared, and so it's just heavy. Okay. On the other hand, the Goldstone is massless because it's a Goldstone. Okay, so that's one way to say it. Okay, you just do the algebra for this model. Okay, but there's a more general question. Okay, I could break the U1 in many different ways. I don't have to start from this Mexican hat. I could have some complicated strong dynamics. Okay, that breaks the U1. Okay, then the question is, why is the Goldstone the only light mode? Okay. But the answer is that it's actually hard to keep scalars light. Okay. The scalars want to be heavy. They're naturally heavy. Okay. So if a scalar is light, usually there's a reason for it to be light. Okay. Scalars are, to keep a scalar light without any symmetry, usually you need to tune, right? So you expect scalars to be heavy. The only reason this theta is light is because it's a Goldstone boson. Okay. If it wasn't a Goldstone boson, it wouldn't be light at all. Okay. Its mass is protected by shift symmetry, so you can't write a potential for it. Okay. That's why it's light. On the other hand, with any other scalar which is not a Goldstone boson, you expect it to be heavy. Okay. And yeah, they usually are. Okay. So that's why we don't think about the additional scalar.
Okay, I don't see any other questions. So Chacko, we have 5 minutes or so.
Yeah, so I have next set of lecture notes. All right. Hold on, what is this? Okay, so, all right, good. So this is the next set of lecture notes. The set 3. So I did send this to you, Rogerio, didn't I? I hope so.
Anyway. I think it's already posted, yeah.
Okay, all right. So, so let me briefly explain what the issue is, because we won't go into this in detail now. Let me explain what the issue is. So in composite Higgs models, precision electroweak constraints require that the compositeness scale be larger than about 5 TeV. On the other hand, the mass of the Higgs is only about 125. So I said, okay, one way to get around that is to make the Higgs a pseudo-Nambu-Goldstone boson. But what you'll see is that even in theories in which the Higgs is a pseudo-Nambu-Goldstone boson, the mass of the Higgs tends to be of order of TeV rather than 100 GeV. Okay, so in other words, the Higgs is lighter than 5 TeV, but it's 1 TeV, okay, not 100 GeV. Okay, so it's lighter, but it's not as light as you need it to be. Okay, and there's a reason for that. It's because, you know, a Goldstone boson is supposed to be derivatively coupled. Okay, it's supposed to have shift symmetries. But the gauge couplings but the Higgs has gauge couplings, it has Yukawa couplings, it has a self-coupling, And none of those are derivatives. Okay, those are not derivative couplings. Okay, those are just regular couplings that don't respect a shift symmetry. Okay, so these couplings, especially the top Yukawa coupling, violate the shift symmetries that protect the mass of the Higgs. Right, and that's a problem. That's a serious problem, right? And so what I'm going to do in the next class is I'm going to show you some methods that address this problem. Okay? I'm going to show you something called a method of reducing the Higgs mass below a TeV using something called collective symmetry breaking. Okay? So any realistic Higgs composite Higgs model that people build today involves collective symmetry breaking, because otherwise it's just too fine-tuned. Okay? So there'll always be something like collective symmetry breaking, or something else I'm going to show you called the twin Higgs mechanism. There'll always be some way to reduce the Higgs mass from a TeV to something closer to 100 GeV. Okay, and so that's what we're going to talk about starting in the next class. Any questions?
Okay, Chacko, so let me, so any questions, guys? So you can either type or, yes, there's a question from Alison. What sort of reactions could we look for that would reveal the compositeness of the Higgs?
That's an excellent question. So the interactions that reveal the composite nature of the Higgs, right, are usually suppressed by the compositeness scale, right? So it's not easy to figure out that the Higgs is a composite just because the compositeness scale is above 5 TeV. Okay? But nevertheless, if you look at detailed processes like di-Higgs, for example, so not single Higgs production, but di-Higgs production at the LHC, for example, then some certain processes like that are sensitive to the composite nature of the Higgs. I have to be a little bit careful, but it's not so much that you're testing that it's a composite, you're actually testing that it's a pseudo Goldstone boson. To really test that it's composite is actually very hard, but you can kind of test that it's a pseudo Goldstone boson by doing precise measurements of its couplings and by looking at things like di-Higgs and things like that.
Okay, yeah. So, any other questions? You can raise your hand or just write in the chat. Okay. Okay, Chacko, I don't see any further questions. Well, thank you very much for this very nice lecture. And sorry, there is a question about. No, I'm not finding homework 1. Does anyone find it? I think it's attached to the first lecture notes. Is that correct, Chacko?
No, I didn't attach it. I sent it separately.
Okay, so I look for it and let you know. So